All right. Well, I hope everybody's having a great day so far. I did hear that it was absolutely necessary that you guys got pulled out of class yesterday. The goods meeting or whatever you want to call it. Okay. Awesome, awesome, awesome. I'm hoping that everybody had the opportunity to go look over the notes and the video that I posted. Okay, so many hands going up. All right, all right. Please be aware, take a look at that material. Come in if you have any questions. The homework is due tomorrow. Yes, sir. Should have one over here. Okay, on the door. The homework is going to be due tomorrow, and we've got several assessments coming up at the end of this week and next week, and I've written them on the board. I've got them on the website as well. I've got next week, the 9th through the 13th taken care of, but this Friday, we're going to have our first CFA quiz. So when I refer to a quiz as CFA, that means that it's a new district policy that I have to give a quiz through Eduphoria. Okay, so the good news is it's going to be multiple choice because I'm not going to trust open-ended on that. So hopefully that'll kind of change things, make it a little easier. But that's going to be over transformations of functions. And if you have the opportunity, if you're not exactly remembering transformations of functions, if you look at this current week, okay, there we go. Transformations of graphs of functions. I did upload a document right there kind of reviewing you over that. All right, and it still has the material for factoring if you want to take a look at that as well. Okay, but that's coming up on Friday. Then on Tuesday of next week, we're going to have our second CFA quiz, but that's going to relate directly to this lesson. It's going to be on limits and end behavior. Okay, so we want to know, very familiar with the vertical asymptotes, holes, things of that nature. When the end behavior, the limit is x approaches positive or negative infinity, all that good stuff. That's coming up on Tuesday. Now, next Thursday, a week from tomorrow, that's when you're actually going to have your open-ended quiz that's going to be very similar to this. Okay, what we actually did talk about in class yesterday. You're going to be asked to find all this information from the intercepts all the way to the domain and range, and then go ahead and graph that without the use of a calculator. Okay, so we are going to be practicing it. We have the whole period today. We have the period tomorrow, probably even on Friday, just to go ahead and get some additional practice in before we go ahead and start equations and inequalities next week. All right, so any questions? All right, so a lot of stuff coming up. So if you have any questions, definitely come on in. Let me help you. Now, this is one of the first things that we talked about yesterday. So let me kind of quickly just go back over it for the folks who weren't here. If you're looking at a rational function and you're trying to determine if it has a horizontal or a slant asymptote, you want to look at what we call the degrees. Okay, well, the degree is the term that has the largest power. Okay, you want to look at that for the numerator and denominator and go ahead and compare the two. And there are three cases. If the numerator's degree is less than the denominator's, as this example shows, degree of 1 over a degree of 2, this is the one time you don't have to do any work. X-axis, y equals 0, will be your horizontal asymptote. Okay, but only if the numerator's degree is less than the denominator's. Second case, what if the degrees are the same? You see, for this example, I have a degree of 2 up top, a degree of 2 in the denominator. In that case, you divide the leading coefficients. Now, when I'm referring to leading coefficients, you want to go ahead and make sure you're using the coefficient that's connected to the term with that largest degree. Okay, I did go ahead and switch these around and said 5 minus 8x squared. So several people throughout the day yesterday told me that the horizontal asymptote would be 5/2. So you want to be careful. You make sure you're using the right values. And then the last one here, last case, if the numerator's degree is greater than the denominator's, there will not be a horizontal, but there will be a what? A slant asymptote. Now, for our purposes, we're going to be looking at linear slant asymptotes, but it is going to be possible, depending on your degrees, you could have a quadratic asymptote, you could have a cubic asymptote, and so forth. In fact, the last problem in this set of notes is going to have a quadratic asymptote. Okay, and then we went through a couple of problems. Now, before I move on, do I need to go ahead and leave this up here for about a few more seconds? I'm not going to leave it up there very long. because I'm hoping that you went to the website and looked over this material because you got pulled out. Please, please, if you ever miss class, go to that website. Okay, that's what it's there for. It's there to help you. Any questions on this? Okay. Okay. And we are going to get the opportunity to look at another slant asymptote today, whether long or synthetic division. Okay, so don't worry about that. Okay, I'm not going to go through this entire problem again. It is online, or if you want to come in during tutorials, have me help you with that. Now, I do realize for the people who were here yesterday, we did get through this problem here, 2B, but I'm going to go ahead and start with this problem again. So the other folks just kind of relax. I want to go ahead and try to catch up the others and have them kind of get used to things. So look at this function right here. It's already factored for me. Does anybody notice anything immediately? There you go. You have a group factor that cancels. So the x minus 2's are out of there. If you have a term or a group factor that cancels, what does that tell you that the function has? It has a hole. There we go. Now, I still need the value of x that's going to make that 0. So x minus 2 equals 0, x equals 2. So I know my hole occurs at 2, but how do I find the y value that it corresponds with? There you go. Plug that 2, the value you got, back into every remaining x that did not cancel. Well, the only thing left is 2x minus 1. So 2 times 2 minus 1 will give me 3. So I know there's got to be a hole here at 2, 3. Okay. Now, technically, there's no longer a denominator because the only expression in the denominator canceled. Okay, but let's just go ahead and keep it as a fraction, 2x minus 1 over 1, just for this next part. Is there any other value of x that would make the denominator 0? What do you think, yes or no? No. Well, so I say yes, that's not what I was looking for. No, there's no other value of x that's going to make that denominator 0. So what does that tell you about, say, the vertical asymptotes? This graph is not going to have one. Okay. The only value of x that made the denominator 0 turned out to be part of a hole. In fact, while this guy did start out looking like a rational function, because the x minus 2 is canceled, it's actually going to turn out to be the graph of what? Linear. It's just going to be a straight line. The only thing left is just 2x minus 1. Okay. Well, let me go ahead and bring up the shortcuts again. If you want to find the x-intercept or intercepts, you want to set the numerator equal to 0. Okay. Well, the only thing left in the numerator is just 2x minus 1. So if 2x minus 1 equals 0, okay, add the 1, divide by 2, x equals what? 1/2. Now remember, always write your intercepts as an ordered pair. Okay. So this one I'm going to go ahead and say 1/2 0. And I'll go ahead and fill this in as we go. So I'm going to go ahead and say 1/2 is right here. Okay. Now, normally, the shortcut for the y-intercepts is to divide the constants. Well, but here, it's just a linear function. If I give you 2x minus 1, what's the y-intercept? -1. Okay, it's that constant right there. So I'm going to put -1. Again, we want to write that as an ordered pair. Okay. And in fact, we have more than enough points to go ahead and see what this guy looks like. So I'll connect those through there. There we go. What about horizontal asymptotes? Will this guy have one? Yeah, there is no denominator anymore, so there is no horizontal asymptote. Okay. Now, linear functions like this, if they have a positive or a negative slope, they are infinitely wide and infinitely tall, but what should I put for the domain? -infinity to 2, the x value of the hole, remember we want to remove him. So -infinity to 2, union 2 to infinity. Now the range is going to look very, very similar, but I'm just going to replace 2 with what? 3. Because vertically I got to remove the 3 again because of that hole. 3 union 3 to infinity. There we go. And then you just always want to make sure to label everything that you can in your graph. So I have the hole here at 2, 3. Okay. This point right here was 1/2 0, and then this point right here was 0, -1. Now, a lot of times, if you have points like this that are really close together, and you're kind of worried about just cramming all that information, you can do like I did, just draw an arrow indicating what that is, but you always, always want to label. Okay. Now, the only other thing I would want to do on this problem is talk about the end behavior. But let's get this next problem done, talk about its end behavior, and then we'll revisit this guy. Okay? So any questions on 2b? Or not 2b? Hey, this may not be English class, but it's going to be lit. Literature. Come on, guys. I'm working hard here. Come on. Okay. Wow. All right. Mr. West knocks another one out of the park. Okay. 3a. Graph and analyze x minus 2 over x squared plus 4. So this one is just giving me the original function. Okay. So my first step, is there any part of this that I can factor? Oh, now be careful. Can I factor the bottom? Why not? There you go. Now, we can factor a difference of two squares. X squared minus 4 would become the conjugates. But x squared plus 4, we don't have a strategy for the sum of squares. This one actually turns out to be prime. In fact, if we were to go ahead and set this denominator equal to 0, x squared plus 4 equals 0. X squared would equal -4. What's about to happen? When I take the square root, it's going to go imaginary. Okay. Now, by setting the denominator equal to 0, this can actually help you with several items. It can help you with vertical and or holes, and it can help you with your domain. But it looks to me there are no values of x that are going to make that denominator 0. Okay, no values of x that I have to throw out. So what's that tell me about my domain? What would it be? Andrew?
Negative to positive.
It is all reals. He says negative to positive infinity. He's absolutely right. Okay. Well, values of x that make the denominator 0, they're either going to become vertical asymptotes or holes. There are no values of x that make the denominator 0, so what does that tell me about my vertical asymptotes and holes? There are none. Okay. So one less thing to worry about on this problem. There's no vertical, and there's no holes. Okay, that's going to make it easy. All right. Well, let's just go ahead and start now at the top and work our way down. Now, remember a second ago I said if you're looking for the x-intercept or intercepts, what do I set equal to 0? Okay, the what? The y. I make y 0? You could do that if you want to, because if I go ahead and set this equal to 0 and solve for x, it's basically going to lead right into that. So you're going to get rid of this denominator, so ultimately you're going to end up with x minus 2 equals 0. Okay. So by setting the numerator equal to 0, that's going to give you your intercepts if there are any. Well, what value of x is going to make that true? 2. Okay. So I know there's an intercept at 2, 0. Okay. So right here. Okay. Now, for the y-intercept, the shortcut I said was to divide your constants. Can anybody tell me what that would end up being? -1/2. Because think about it, if x is 0, you're looking for the y-intercept. If those terms disappear, all that would be left are your constants. So -2/4 is -1/2. Okay, so 0, -1/2. Let me go ahead and plot this point right here. Okay. What about a horizontal asymptote? Do we have one? Why is it 0? There you go. Look at the degrees. Those 3 cases we started with. Will.
So if you have a horizontal asymptote at y equals 0, then does that make your x-intercepts null?
No, it does not. Because for one very important reason. So I'll come back to that. Okay. So the degree up top is 1. The degree down below is 2. Because the numerator's degree is smaller than the denominator's, Connor's absolutely right. We do have a y equals 0. Now here's the thing. Okay, this is what Will was asking about. Okay. When you draw the horizontal asymptote, Is it okay if you draw it all the way through? You are more than welcome to do so. But this is one graph that kind of illustrates why I don't do that. Okay. Every time I draw a horizontal asymptote, I'm only going to draw the left end and I'm going to draw the right end. Okay. Because remember we talked about this starting last Friday, the horizontal asymptote doesn't exist around the origin. It only begins to exist as you push out to positive and negative infinity. As the x values get larger, or as the y values get smaller, or as the x values get smaller, as they get larger or smaller. Okay. Because remember, if you go ahead and draw the horizontal asymptote all the way through, that's perfectly fine. But if you go ahead and then draw your sketch, it's going to look like your graph is doing what? Looks like it's actually cutting through the asymptote. We know that will never happen. Okay. So that's the reason I go ahead and do it that way, but I'll leave it up to you. Clarissa? How do we find the horizontal asymptote? Somebody help me out. We looked at the degrees. Okay. Up top, you've got an x to the first. Down below, you got an x squared. We're looking for the largest power in the numerator and the denominator. We want to compare those. Here, we see that the numerator's power is smaller than the denominator's. So this previous page, that turns out to be case 1. The numerator's degree is less than the denominator, so I know it's got to be the x-axis. Okay. So comparing those powers is going to tell you whether you have a horizontal or a slant. Now, let's talk about this guy right here. We need to be able to graph this guy without the use of a calculator. So let's say as x goes to negative infinity. Let's take care of the left side of this first. Okay. Well, there's really two options. The graph is going to approach this horizontal asymptote either from above or from below. So either he's going to look something like this, or he's going to look something like this. Is there a problem with one of those? Which one can he not do? Can he not approach it from below, or can he not approach it from above? What's wrong with above? Okay. Remember, what was the x-intercept we found? We only found the one x-intercept, right? If this guy was meant to approach 0 from above, what would he have to do? He would have to cross the x-axis. We should have been able to find another intercept. Because we don't have that, that tells me he has to approach it from below. Okay. So where do you think I'm going to connect this negative 1/2 to now? What would be the next logical place? Okay, Andrew? I'd go ahead and connect it to the next intercept right there. Now we have another decision to make. Okay. As this graph continues to the right, he's going to want to get close to that asymptote. So again, do you think he's going to get close from above or below? Why above? Okay. Well, the way I drew it doesn't really indicate it, but if I were to approach it from below, see, he's already crossing the x-axis. He would have to cross the x-axis again. So it's the same reasoning that we did before to help me figure out where that portion is going to go. This guy has to cross from above. Okay, so the graph's going to look something like that. Okay. In fact, let's see how close we got. If I come over here, control divide, what do we have? X minus 2 over x squared plus 4. There we go. So as x approaches negative infinity, it's approaching 0 from below. As x approaches positive infinity, it's approaching 0, the horizontal asymptote, from above. Okay. So kind of think of these sometimes, they're almost like puzzles. Okay, you got to put the information together where it makes sense in your graph, and you're just trying to figure out, a good sketch of it. Is there anything I forgot to do here? Like if I were to turn this in, would I receive 100% for it? No, why not? I didn't label. Okay, always label. Well, I got an asymptote, y equals 0. I have a y-intercept here, 0, negative 1/2, and then an x-intercept, 2, 0. Okay. Always label all the information that you're finding. Now, the end behavior, we already talked about. Okay, now we just need to write it down. When you're asked about the end behavior, this is the limit as x either approaches positive infinity or the limit as x approaches negative infinity. Okay. Typically, for end behavior, you really want to focus on the horizontal asymptote. Okay. So in this case, whether x becomes extremely large or extremely small, what's the graph doing as x does that? It's getting closer to what? It's getting closer to 0, that horizontal asymptote. Okay. Now, this is why I wanted to wait on the end behavior for that first one. Okay, so let me go back real fast. Let's take a look at the end behavior for this line. So the limit as x goes to positive infinity, the limit as x goes to negative infinity. Okay. Now, it's true for those statements, you really want to focus on the horizontal asymptotes. But what do you notice about this graph? He doesn't have any horizontal asymptotes. Right, Caleb? Okay. So think about it. As x becomes extremely large, well, what's the function doing? It's not approaching something, but it is doing what? Who said it? What is it? Somebody said something. Who said it? Kate? It's getting bigger. How big? It's never going to stop. So as x approaches infinity, the limit will be infinity because the y's are going to increase without bound. So what happens as you go to negative infinity? What's the graph doing? Yeah, he's going to decrease without bound. Okay. So sometimes you just have to look at the behavior of the graph if there's no horizontal asymptote. Okay. How we doing? Is a lot of this coming back from Algebra 2? Good times? Of course they were. Okay. All right. Now, what I've been doing in the other classes is I've had people giving you 5 minutes, and then I've had people come up and show me the information, how they found it. I've had people go ahead and sketch the graph for me. I'm not going to do that for you folks because pretty much everybody was gone yesterday for that assembly. All right, so again, I'm going to go ahead and work it with you, but a lot of this, you guys are going to give me direction. You're going to tell me what to do. All right. Now, let's take a look. 2x squared minus 3x plus 5 over x minus 2. I want to find all this information, and I want to go ahead and get a pretty good idea of what the graph's going to look like. Remember, no calculator. Okay? No calculator. We want to get as far as we can without that. So what's a good starting point? What do you recommend I do? Factor? Okay, let's start to factor. Now, 2x squared minus 3x plus 5. Now, remember, the method I like to factor a trinomial, what's that called? My father drives a red Mercedes convertible. Okay, so however you decide to do it, I'm going to do it that way. So 2 times 5 will give me 10. Now, I need 2 factors that's going to multiply to give me 10, but add to give me negative 3. Well, do you notice a problem? Okay, see, because 10 is positive, well, that means I'm either dealing with 2 positive factors or I'm dealing with 2 negative. Now, 5 and 2, you can subtract them to get the 3, but they would have to be different signs. So what are we thinking about this numerator? Can he be factored? No, he's going to turn out to be prime. Now, just because you can't factor him doesn't mean that he still won't cross the x-axis. So you want to be careful. Okay, I would choose another method just to be sure that I don't get some decimal values. Okay, we have completing the square, we have the quadratic formula. Just for the sake of time, I'm going to say quadratic formula. Okay, what is that? Opposite of b. Woo. B squared. There you go. How many people your teacher taught you to sing that? The opposite of b plus, yeah, okay. There's always some teachers that do that. That's great. I'm just kind of curious off topic here. What do we call b squared minus 4ac? It starts with a d. That is the discriminant. Very good. Okay. Now, let's go ahead and plug in. We've got A, B, and C. So the opposite of B, that's a positive 3, plus or minus the square root. B squared would be 9, minus 4 times A times C, okay, all divided by 2 times A, 4. Okay. Well, there's one part of this I'm going to be really interested in. What is 9 minus 4 times 2 times 5? Negative 31. Okay. When I take the square root of a negative, that's going imaginary. Okay. So if I were to graph, forget about the rest of the function, if I just took that numerator and sketched him, that quadratic will not be doing what? What's he not coming into contact with? He is not coming into contact with the x-axis. Okay. So knowing that, what does that immediately tell me about my x-intercepts? There are no values of x that will make that 0. So Connor's right. There are no x-intercepts. Okay. Would I still have a y-intercept? Remember, what was the shortcut? Divide the constants. Okay. So if every x is replaced with 0, if they disappear, you divide your constants. So just negative 5 halves. Or if you want to say negative 2.5, that's fine. Okay. Now, for vertical asymptotes, holes, and the domain, what would you need to set equal to 0? What's the only part we haven't? The denominator. We started by setting the numerator equal to 0. Okay, so my denominator, x minus 2 is equal to 0. So x equals 2. Well, now we have to make a decision. Is that 2 a vertical asymptote, or does he belong to a hole, a removable discontinuity? Why isn't he a hole? Remember, the top part didn't factor. There was no cancellation, no simplifying. So that tells me the good news, there's no hole. But I do have a vertical asymptote at x equals 2. And remember, for the asymptotes, always give me the equation, x equals or y equals. Okay. Now, how do I know this one will have a slant or oblique asymptote? The greater degree up top. Okay. Numerator has a degree of 2, denominator has a degree of 1. Now, we're going to have to figure out what that slant asymptote is. All right, so I'll let you guys decide. Would you like me to use long division or synthetic division? I'm actually hearing both. How many people want long? Okay, 1, 2, 2. How many people want synthetic? Okay, synthetic it is. Now, I would encourage you, if you did raise your hand for long division, I would still encourage you to go ahead and do it, because what should happen? You're going to get the exact same thing, or at least you should. Okay, so here's a synthetic division. I'm going to create a little box in my top left corner, and I'm going to draw a line. Okay. What number will I put in the box? And is it important? It is very important, so how do I figure him out? There you go. I'm looking for the number that makes your denominator 0. Well, we know that's 2. My denominator is going to be my divisor. We're going to divide x minus 2 into the numerator. Okay, so what am I going to put to the right of this box? There you go. Now remember, it's got to be in standard form or decreasing order of your powers. If any term is missing, you want to plug a 0 in there to account for that. So here, 2x squared minus 3x plus 5, I'm going to put the 2, the negative 3, and then the 5. Okay. How do I perform synthetic division? What do I do? Okay, so the first number outside the box drops. Okay. Now what? There you go. If I'm below the line, you multiply by the box. If I'm above, I add. So basically, I just continue to fill in all the columns until they're done. So 2 times 2, 4 plus negative 3. 1 times 2 plus 5, 7. Now, 7 is my what? Okay, the very last number, okay, at the bottom of the final row, that's going to be your remainder. We don't care about the remainder. Now, there's going to be some other teachers who are going to tell you, mathematically, put that over your divisor. There's ways to write it. I'm just interested in you finding the slant asymptote, which is going to be created using these guys here. Now, remember, your answer, your quotient, always starts 1 degree less than what your dividend started with. So he started with an x squared. So this guy starts with x to the first, and then we have our constant. So what's my slant asymptote? 2x plus 1. There we go. Okay. All right. Do we have enough information to go ahead and label the domain? Okay, what would it be? Negative infinity to 2. Union 2 to infinity. Okay. Now, unfortunately, we don't have enough information to go ahead and determine the range yet. Okay. This is a type of problem where if you have a good knowledge of calculus, you could probably go ahead and do it by hand, or you'd have to use technology. You'd have to use the calculator. Okay, but we're not using the calculator. So the very last thing I'm going to do is show you about that range. Okay. Now, the quiz you got coming up next Thursday, where you're going to have to do one of these by hand, you should be able to do it by hand. Okay, there should be no problem. You won't have to use calculus or technology. This one's just kind of the exception. Okay, so we got to wait on that. All right, well, let's go ahead and start to put all this together. We have a vertical asymptote at 2. Okay, so there's x equals 2. We had our slant asymptote at 2x plus 1. So that crosses at 1, up 2 over 1. Okay. So that's y equals 2x plus 1. Remember, always label, always label. Then we have the y-intercept at a negative 5/2, so a negative 2.5. Okay. Now I'll go ahead and label that at the end. Now, you remember, well, actually, no, you wouldn't remember because you were here when we did it yesterday, which is why I'm really going to encourage you to watch that video if you need to perform an analysis of the vertical asymptote. But we need to understand what the behavior, what's the graph doing as I approach 2 from both sides. Okay, so I'll go ahead and do one of these for you. Let's say the limit as x approaches 2 from the left. You guys remember, if we put a plus or minus as the power, that indicates the direction that we're coming from. Okay. Now, what I was explaining to the other classes was if I want to analyze the behavior around a vertical asymptote, I want to choose a value to the immediate right and left of that undefined value. I use 1/10 of a point. So I'm going to go ahead and say, if I'm going to look at 2, well, then above that would be 2.1. What would be 1/10 below? 1.9. Okay. Now, the idea is I'm going to take that value and I'm going to plug it back into the original function. Okay. All I'm interested in, are you going to get a positive or a negative value? Okay. So let's see what would happen here. I'm going to mimic this. All right. So we have one group up top. We have one group down below. So let's start with the easier one. If I take a positive 1.9 and I plug it in for x, what's a 1.9 minus 2? Negative 0.1. But the fact is it's negative. Okay. Not interested in what the actual number is. You're more than welcome to calculate that. But this is going to lead into what we're doing next week, sign charts. I'm only interested in the sign. So what do you think I'm going to do now? I'm going to take the 1.9 and I'm going to plug it in for every x up top. So basically I'm going to have 2 times 1.9 squared minus 3 times 1.9 plus 5. So it doesn't matter to me what the actual value is. Will it be positive or negative? That will be positive. Okay. So what's a positive divided by a negative? So I know this guy wants to go to negative infinity. Remember, we first did this last Friday. If you're looking at the left and right sides of a vertical asymptote, there's only 2 choices. The graph's either going to go up to positive infinity or he's going to go down to negative infinity. So what I'm doing is I'm figuring out what this guy's behavior is. So see, I put a little mark right here to the left of 2 to indicate that he wants to curve down. Okay. Well, where do you think this guy is going to be? Let me go ahead and label these regions. Let's say this is region 1, 2, 3, 4. Okay. Which region guaranteed should have one of my branches? Why are we focused on 2? Yeah, not only is there a y-intercept there, but we saw that he wants to curve down. Okay, so I'm probably going to have something looks like this. Okay. See, even though he's in this region, he was going to want to get as close to those 2 asymptotes as he can. Right, Caleb? Okay. All right. Now, I'll go ahead and do the analysis for the other side, the 2.1, in just a minute. But sometimes it's not always necessary. Would you say the other branch has to go in 3 or 4? A lot of people are saying 4. What's wrong with 3? Let's just say, for argument's sake, that there was a branch that looked like that. Is there anything wrong with that? Will, say it again. If the branch would be here, he would have to cross the x-axis, right? But what did we find out? There are no x-intercepts. So see, sometimes you may not need to do this analysis. If it helps you, absolutely. So I'm going to guess that there should be a branch up here that's going to try to get as close to those asymptotes as you can. Now, remember, this is just a sketch. Maybe I drew that a little lower than I should have. Maybe I drew it higher than it should have. I'm not interested in that. Okay? But you can see why I'd have to use something specific in order to figure out the range, because I need to know where this guy stops and where that other one begins. Okay? Let's go ahead and do that analysis. So I took care of the 1.9. Okay? What happened on the right side of 2? Did the curve up or did it curve down? Curved up, so I should be getting a positive infinity, right? So let's see if that's what happens. The limit as x approaches 2 from the right. Okay. So what did I choose to the right of 2? 2.1. I'm going to go ahead and plug those in just like I did before. See, I'm going to mimic the groups I have with signs. Let's start with the easy one. What's a 2.1 minus 2? That's definitely a positive. Okay. Now, let's take a look at the other one. 2 times 2.1 squared minus 3 times 2.1 plus 5. Would that end up being a positive or a negative? Yeah, the sum of those 2 positives is definitely going to be bigger than that one negative portion. Doesn't matter what it is. What's a positive over a positive? There you go. So there are methods you can use to analyze if you're not sure. If there aren't enough clues to figure out where your branches should go. Okay. How we doing? Anybody lost? Anybody not sure about anything I did here? Hey.
Where'd you get those?
I chose those. Now, that's just a personal preference. I like to choose a value as close to the vertical asymptote as possible. I got in the habit of just choosing one within 1/10 of a point above and below. So let me give you an example. Let's say you run into another problem. Let's say you have a vertical asymptote that's, I don't know, x equals -4. Okay. I want to choose 1/10 above and 1/10 of a point below. So what would be on the right side? Oh, gotta be careful. -3.9. Because that's going to be larger than -4. So now on the left side, that's where I would choose the -4.1. Now, like I said, that's a personal preference. I always like to go 1/10 of a point above and below. Okay. That's something I've been doing for a very long time. All right. Okay, now let me go ahead and help you with the range here. Because like I said, we're definitely not going to be doing that by hand. So why don't we go ahead and plug this guy in. All right, so document B. Let's get back over here. Control divide. It was 2x squared. Was it -3x plus 5? Over x minus 2. Okay. So let's see how well we did. Well, we definitely got this guy right here. Now, we don't see the upper branch So let me go ahead. Okay, let's zoom out just a little bit. Okay, maybe I didn't choose that. Window zoom, zoom out. There we go. Okay, so now we see the bottom portion of it. That should suffice. Let me go ahead and move this guy out of the way. Now, one other thing you can do, you could, if you want to kind of help, actually see what's going on, you could go ahead and plug in the equation for your slant asymptote. Okay. You could even, there's a way in the Inspire to go ahead and put a vertical line in there. Right, Caleb? Caleb, you need a drink of water or something? You sure? You really sure? Okay. Just looking out for you, man. Okay. All right. So we need to figure out what these guys are doing right here. So do you remember how in that first week of school I showed you to find the relative maximum and minimum values? How would I do that here? Let's say I wanted to find this guy. How do I do that? Menu, analyze graph, minimum or maximum. Let's find the relative maximum first. So this guy. Now, the only difference is because it's made of these two different branches, it's asking you which graph. So it's telling you basically which one do you want to start at. So I want to start on this one right here. As soon as I choose, now it says what? Lower bound. Okay, so I'm going to move the vertical line to the left of where I believe that point is. Upper bound, I'm going to slide it to the right. See, there we go. Okay. In fact, let me go ahead and just write this out. You would do the same thing for the other one, but this point right here, okay, ends up being, that is 0.129, and then it was a negative 2.48. And this point up here, I think I'm a little further off on it, yeah. This one here should be a 3.87 for the X value, and then a 12.48 for the Y. So I definitely went further down on that branch than I needed to go. Okay. So now that we know those points, well, I should be able to give myself the range. Negative infinity to, well, the first one stops at negative 2.48. Union. Where does the other one pick up? 12.48, and then goes to infinity. Okay. Now remember, I will not be giving you one of these on that quiz next week. Okay, I will definitely give you one that you should be able to take care of by hand. Seems pretty rational, right? Yeah. It's a rational graph. Sandra, you like that one, didn't you? Of course she does. Okay, all right. So the only thing left is the end behavior. Okay. So what am I talking about when I say end behavior? This is x approaching what? Okay, positive and negative infinity. So the limit as x approaches negative infinity. Now again, typically with these, you want to go ahead and look at the horizontal asymptote. But there's no horizontal asymptote here. Okay. This guy's got a slant. So again, compare it to that first one we did today, the linear function. As the x values become increasingly large, well, what are those y values going to continue to do? They're going to become infinitely large too. They're going to get closer to that line 2x plus 1, but they're going to continue to increase in size. Well, what happens as we go to negative infinity? Y will decrease without bound. Okay. Questions? How are we doing? Is this coming back to you? Okay. Now remember, the homework is due tomorrow, but we will have the opportunity to practice a few more of these. Okay, we'll probably have ourselves a focus activity, and then we'll move on from there. Okay. Any questions? All right.